going to talk about collective communication in MPI, which is the subject of chapter number 6. Whoops. The subject of chapter number 6 in MPI standard. It's a very lengthy chapter, so we're going to spend some time on this chapter. And we're going to have the same drill as chapter number 5, which we ended up basically breaking down every episode into like digestible chunks of 23 to 25 minutes, which is probably the best amount of time that I can get your focused attention. We're going to do the same here, but beforehand, I have no idea how many parts we're going to need for this collective communication. So we kind of want to go with the flow, and we're going to spend time up until 23 to 25 minutes and then chop off every video to create a new episode. I have prepared a couple of examples for today. We're going to take a look at the blocking ones for today. Let's go with ls minus L and vc minus L. So we have 23 examples prepared for today, which most probably, like 100%, it's going to be divided into several episodes. We cannot cover it all in one video. But anyways, let's jump into it. Collective communication. What do we mean by collective communication? So the standard says collective communication is defined as communication that involves a group or groups of MPI processes. Oh, sounds interesting. The functions of this type provided by MPI are the following. So you can take a look at this to have an idea what kind of sort of operations, communication operations, we're going to basically dealing with. So we have MPI barrier, and MPI I barrier, MPI barrier init. So you can, by the look of it, you can know that this one is most probably a blocking call, and this one with the I. Preceding I basically means that you have a non-blocking version of it, and this MPI barrier init seems like an initialization step, which means persistent communication, right? So barrier synchronization across all members of a group. So it's sort of a barrier synchronization. Yeah, meaning is quite obvious. MPI bcast, MPI I bcast, and MPI bcast init. So this is broadcasting from one member to all members of a group. This is shown as broadcast in figure 6.1. We're going to take a look at that figure in a moment. Next category is MPI gather, MPI I gather, MPI gather init, MPI gather v, MPI I gather v, and MPI gather v init. So again, we have the same drill. We have the blocking call, we have non-blocking call, we have the persistent version, and then we have a v version. We're going to see what does that mean. But all of these families of sort of communication operations, they gather data from all members of a group to one member of that group. So this is shown as gather in figure 6.1. Next one, MPI scatter, and all the relative ones. I'm not going to pronounce everything. So scatter data from one member to all members of a group. So this is sort of the reverse of gathering, right? In gathering, everybody basically participates in sending information, and one sort of process gets all the information. In scattering is sort of the reverse of this process. So one process has all the information in the world, and that one process wants to scatter that information into smaller chunks and then feed it to other processes. Then we have all gather, and then all these variations of all, preceding all with all those other methods. So we have a variation on gather where all members of a group receive the results. So in this family, one member is going to get the result. And in the next family, which has the preceding all, as the name all suggests, so everybody is going to receive the final result. The next family is all to all, and all its sort of variations of it, with including V in the end, including W in the end. Yeah, and all those different types. So that is a scatter gather, data from all members to all members of a group. This is also called as complete exchange. And you can see it also shown as complete exchange in this figure 6.1. Figure 6.1 seems to be a very important figure. We're going to see it in a second. And then we have all reduce. So these are, today probably we're not going to talk about this reduce operation, but these are the reduce operations. So these are global reduction operations such as sum, max, minimum, or any user-defined functions where the result is returned to all members of a group These are the variations with all, or we have a variation that the result is only returned to one member, that is MPI reduce, for example, or MPI reduce, or the persistent version. Then we have another family, such as MPI reduce scatter block and MPI reduce scatter. So this family is sort of a combined reduction and scatter operation. And finally, we have MPI scan, I scan. So this is inclusive scan and an exclusive scan. So scan across all members of a group, and that is also called as prefix. Okay, before going into this figure, this is figure 6.1. Before going into that, let's take a look at these sections. One of the key arguments that you always need to pass around when you're working with collective communications is sort of the communicator, because communicator gives you the context of communication. It basically tells you on what grounds, on what context you are basically trying to communicate between which processes, which groups, which people are going to communicate with each other. And that is sort of the communicator, which is super, super important. We haven't talked about groups, communicators, and stuff like that, which is the subject of next chapter. But this chapter, so we're going to have a very vague definition of it, or we're not going to mess around with it that much. It's going to be sort of a black box for us. But we're going to use it in our examples, but we're not going to pay attention to it up until to the point that we talk about it in chapter number 7. Okay. So then we said the syntax and semantics of the collective operations are defined to be consistent with the syntax and semantics of the point-point operations. So let's say congratulations. If you already know the semantics of point-to-point communication, then most probably it's going to be easy for you to understand the semantics and syntax of collective communications. So several collective routines such as broadcast and gather, we already talked about it. They have one originating or one receiving MPI process, such as MPI. That MPI process, such an MPI process is also called as root. Some arguments in the collective functions are specified as significant only at root and are ignored for all participants except the root. So we're going to see various examples of this thing. So you're going to send, for example, like hundreds of parameters into one, let's say, communication operation, but only, let's say, a collection of them is important at other processes. But most of the times, like 100% of those parameters are important for the root process. Okay. Type matching conditions for collective operations are more strict than the corresponding conditions between the sender and receiver in point-to-point communications. Namely, for collective communications or for collective operations, the amount of data sent must exactly match the amount of data specified by the receiver. So we have already seen in the chapter regarding point-to-point communication that the receive buffer can have like any size it wants, but it needs to, it doesn't have to basically fill up all that space. So that is the difference. But in collective communication, the receive buffer must be sort of the same size as the amount of data that you sent. So type matching is a little bit more stricter here. A blocking operation is complete as soon as the call returns. A non-blocking or immediate call requires a separate completion call. This is similar to what we've seen in point-to-point communications. And the completion of a collective operation indicates that the caller is free to modify locations in the communication buffer. Either it's going to be receive buffer, which it means that it can read or access those data, or it's going to be a send buffer, which you can basically access that to manipulate it or change it. It doesn't indicate that other MPI processes in the group have completed or even started their operation, unless otherwise is implied by the description of the operation that we are looking at. Thus, a collective communication operation may or may not have the effect of synchronization or synchronizing all participating MPI processes. So you should not rely on the synchronization side effect of these sort of collective calls. MPI guarantees that messages generated on behalf of collective communication calls will not be confused with messages generated by point-to-point communications. Okay. So another hint is that in collective operations do not have a message tag argument. So there we go. That's one key difference with point-to-point communications. The statements about synchronization are made so as to allow a variety of implementations of collective functions. So that is some rationale which we don't care. So now this very important figure. So take a look at this very simple and beautiful diagram. It's a square sort of by 1, 2, 3, 4, 5, 6, 6 by 6, sort of a square grid here. So from left to right, it shows data sort of buffers. And from top to bottom, it shows, for example, processes, process number 0, process number 1, all the way to process number 5, which is 0 to 5, 6 processes. So broadcasting means that the root process or somebody that has that information is going to broadcast and like inform all the processes in that group with the same information that he or she has. So this is basically what broadcasting means. So you can visually see it, and then you understand so easily what broadcasting means. So this is the effect of broadcasting. So what is the effect of a scatter? So the family of operations called scatter means that, let's say the root process has one data buffer which has 6 elements, A1, A0 to A5. So this is process number 0 or root process. If we scatter data, so every sort of process based on the rank, for example, A1 has the index 1, so this, let's say, data goes to rank number 1. So that is why A1 goes here. And A2 has the index number 2, goes to process number 2, and all the way to process number 5. That is a scattering. And gathering is exactly the opposite. So here, all processes in gathering, all processes have, let's say, a portion of the data, and after gathering, one process, which is the root process, is gonna have all the information in the world. So scatter and gather is sort of, that's why we said these two operations are sort of the reverse of each other. And then finally, all gather. Let's say every process has a chunk of information, and once you do all gather, so every process is going to have all the information. So A0, B0, C0, D0, E0, and F0 are going to get replicated basically into let's say, receive buffer of process number 0 in the way that each rank is going to occupy the same buffer. Let's say B comes here because B has rank 1, and this is going to be sort of, let's say, not rank 1, but it's going to be element number 1 in the array buffer of process number 0. That is why we have this harmony of A, B, C, D, E, F. Okay, complete exchange is that, let's say, all processes have their own informations and they want to basically get, like it's like a mishmash of everything. So that's the complete exchange. And we saw that in this family of sort of operations, like all to all and all the other variations, they're also called as complete exchange. So just take a look at the pattern, like A0 to A5 and then A0. It's going to get this one from rank number 1. It's going to get this one from rank number 2. It's going to get this one from rank number 3. This is how it looks. So now we have sort of a series of A to F for every process. Okay. Advice to users: it is dangerous to rely on synchronization side effects. This is what I already mentioned of the collective operations for program correctness. For example, even though a particular implementation may provide a broadcast routine with a side effect of synchronization, the standard doesn't require that. So do not sort of rely on that sort of synchronization side effects. Okay. Now we go to communicator argument, which we said sort of a key argument in more or less every collective operation that we have, because it gives you the context of sort of communication. We haven't talked about communicators As I said, also here it mentions that it's going to be in full detail in chapter 7 described. But for the purpose of this chapter, the only thing we need to know is that we're going to have intracommunicator and intercommunicator. This is sort of the thing that we learned in chemistry or physics, let's say molecular physics or so, that they say we have intermolecular forces and intramolecular forces. So intramolecular forces are the forces inside an atom or inside inside an atom, and intermolecular forces are sort of the forces which are between two molecules. Okay, so here we have also the same context. So when we talk about intracommunicator, it means that all the members inside one single chunk or one single group. And when we are talking about intercommunicator, it means that imagine in your mind that we have two separate communicators or two separate group of processes. And these two separate group of processes, somehow they want to communicate with each other. But in intracommunicator, so you should imagine only one group of processes, and let's say communication wants to happen within the context of that sort of processes. Okay, so these are related to specifics related to intracommunicator. All MPI processes in the group identified by intracommunicator must call the collective routine. So this is very important. Everybody needs to call that routine. And there's also an option of in place for intracommunicator with the output buffer being identical to the input buffer. This is specified by providing a special argument called as MPI in place. We're going to see examples of this one quite a lot through the examples. Okay, let's move in. Then we have applying collective operation to intercommunicators. So now if you want to understand collective operations that apply to intercommunicators, first you need to take a look at the most MPI intra-communicator collective operations. And these are falling into these categories. So the first category is all-to-all. This means that all MPI processes contribute to the result and all MPI processes will receive the result. And these are all sort of those communication routines that follow this all-to-all sort of paradigm. Then we have all-to-one category. This means that all MPI processes are going to contribute to the result, but only one process is going to get that result. So these are the sort of those routines that follow this sort of paradigm. And then one-to-all means that one MPI process contributes to the results. All MPI processes will receive the result. That is sort of like broadcasting, scattering, and stuff like that. And then we have one family which doesn't fall in any of those, all-to-all, all-to-one, or one-to-all, which means collective operations that do not fit into any of these. And these are like inclusive scan and exclusive scan. Okay. Okay, it says, let's see, what is this one? For example, an all-to-all MPI all-gather operation can be described as collecting data from all members of one group with the result appearing in all members of the other group. So this is one example of all-gather. So this is an all-to-all operation. So all processes are going to contribute in the result, and all processes are going to receive that result. So the following collective operations also apply to intercommunicators. So these are all sort of communication operations that also apply into intercommunicators. So this means that you can use these operations once you want to talk between two separate communicators, let's say. Now we have the specifics of intercommunicator. So all MPI processes in both groups, A and B, let's say, identified by the intercommunicator, must call the collective routine. This is super important. And notice that the in-place option for intracommunicator doesn't apply to intercommunicators. So this is one key sort of difference, since in the intercommunicator case, there is no communication from an MPI process to itself. That is the key difference, why we don't have in place. So in place means that you could use one buffer for sending and receiving, but since we don't have in intercommunicator, no process is going to communicate with itself, then that is why you cannot have that option of MPI in place. Okay. Then I have something here, which probably was something important for this. The root uses the special value MPI root. All other MPI processes. Oh, this is also important. Like once you want to have this intercommunicator, then it says that the group containing the root, let's say group A, all MPI processes in the group must call the routine using a special argument for the root, and the root itself needs to use the option MPI root. All the other processes which are in group A with that root, they need to use the option MPI proc null. And the other processes which are in the other group, they all need to pass the rank of basically root process in group A. So we're going to see all these things in a second. So these examples might not, like these explanations might not sound clear right now, but we're going to see examples for them. So this is, again, a visual example that you can understand like quite nicely. It says intercommunicator all gather. This means that this is the left communicator, this is the right communicator. Processes 0 through 3, which is 4 processes, they all have sort of one chunk of information which is interested for us. All gather means that every process in this family of communicator, which is L communicator, left communicator, are going to put their information together, which is going to be 1, 1, 1, 1. It's going to be a block of 4. That is the block of 4 here. And they're going to send this block of 4 to every process which is in the right communicator. Process 0, process 1, process 2. Note that when you are working with different communicator, each communicator has its own sort of ranking system. So you remember that we had ranks 0 from n minus 1, n being the number of processes. So the same story goes here, but every communicator is going to have its own private ranking system. And in return, so this is one direction of information passing from left communicator to the right communicator. The same story happens from right to left as well. So this has one bit of information, this is one bit of information, this is one bit of information. You collect those 3 and then you generate this block of 3 and then you pass this block of 3 to all of those processes in the left communicator. So now every process is going to have sort of a copy of that information. So that is sort of the concept of those all-to-all sort of communication patterns, which they are bidirectional. So you can see like we have information from left to right, and then subsequently we have information passing from right to left. And I also mentioned it here, all-to-all, it always has bidirectional data transfer sort of layout. And one-to-all or all-to-one, it always has sort of a unidirectional nature to it. Whoops. So this is already 23 minutes. We're gonna stop here and are gonna continue in the next episode.